All right, so my name is LJ Wabker. I'm a principal TME in SP&S, which is whatever we call the big router business unit this week. We seem to change names more often than I change jobs. So at one point I had a set of business cards printed that just said Highway Train Network Monkey, and I figured that was easier to just leave that there than try to keep up. So we'll talk a little bit in detail about the system. If anybody online watching this is in Barcelona and wants to come hang out this afternoon at the breakout session, we're going to do these slides and a few more for the group here. But what we're going to talk about is just kind of an introduction to the technical part of the technical side of the systems, talk a little more detail about the Cisco Silicon One, which is the new NPU, the new ASIC that powers the system. Try to give folks a little bit of an idea of what the kind of technology challenges that we have to solve trying to build systems that go this big and go this fast. The key theme, I guess, when you build a system like this ends up being what trade-offs are you going to make to, everybody wants it to go faster, everybody wants it to use less power, everybody wants it to be cheaper. At some point, you can't choose all three of those things at the same time. So a lot of building systems, especially when you get out to the edge of some of these parameters, is about making trade-offs that kind of make sense. And then we'll talk a little bit about what we're looking for moving forward in terms of the next 2 to 4 years. After that, we'll segue into Mark Nola's got some excellent material on how we're going to do 400 gig optics in the optical domain. So start out, why do we need a new chip, right? The answer is, well, you don't necessarily need a new chip if everything that the old chip does is fine forever. We don't tend to work in an industry that supports maintaining things forever. Obviously, the requirements change. Everybody wants to build bigger networks. Everybody wants to build faster networks. In large part, this kind of architectural shift has either been enabled or demanded by the growth of the mega-scale cloud providers. And some people think that's a terrible idea, and some people think that's a great idea. The reality of the market is that the networks that are being built in that space are orders of magnitude larger and orders of magnitude higher bandwidth than what most of the market was building 5 or 10 years ago. And so there's been a tremendous amount of kind of both implicit and explicit change in how those networks are built. And it's that those changes have flowed down into kind of the supply chain and how people are asking us to build these really big systems. With the scale out of these networks, there's a meaningful increase in the amount of attention that people are paying to bandwidth that gets delivered and how much power it takes. As you look at kind of the TCO type calculations for a lot of these big networks, the amount of money that people are spending on power in often cases is comparable to, or in some cases even outstrips, what they're paying on the systems themselves. So building systems that are power efficient and allow the people who are deploying them to make the trade-offs that they want to make in terms of where do I need to burn watts that's going to actually either save me money or make me money, depending on which side of that you're on. And then again, that's driven primarily by the hyperscale cloud players, and a lot of the technology and innovation that's been developed to support those very, very large networks is now flowing down into the rest of the ecosystem, and everybody else kind of gets to benefit from that. We'll talk a little bit about some of the changes in the underlying component technologies. These are all the little bits and pieces that the serious hardware nerds, of which I only pretend to be one, have to think about in terms of how are we going to build these systems, how are we going to make everything fit. So we'll talk about those. An ASIC architecture, if you'll let me kind of bastardize that term a little bit, usually lasts somewhere around 10 to 15 years. So when we started looking at the program and kind of looking at what was available in the market, some of which had been completely designed by Cisco, some of which had been partially designed by Cisco, and some of which was purchased through merchant silicon providers, we took a look and said, we don't have a really good view on where the silicon's going to be in the 2020s. We had a really good, this was about 5 or 6 years ago when we kind of sat down and got a meeting of the minds and did some of the math and said, we're not sure what's going to exist in the 2020s, and so we're going to have to start looking at different, or things that give us options of how to build some of these systems differently. So as you start thinking about what does the chip need to do, or what kind of chip do you need to go out and get, you think about things, where is it going to be deployed? To what extent does it have to have feature parity? I've been building and supporting big routers now for almost 25 years, and one of the things that people have had to get used to is, in the old days, new routers had all the features as the old routers. And over the last 15 to 20 years, that has changed to where now new routers, certainly when they first ship, don't have all the features that the old routers do. And there's always a couple of things that if you want to go another order of magnitude faster, you're not going to be able to do whatever feature you used to do. So people have started both designing and building networks differently. So we have to think about how we're going to deliver the features that people absolutely can't live without, and how we're going to help people get away from the features that they're going to have to live without if they want to do, in 2020, what you're talking about being hundreds of terabits in a single system. And then you have to think about things where, what kind of life support, what kind of lifespan are you going to have for a chip like this? We go and build something like this. You can't spend the amount of money that it takes to design a chip this complex and do one iteration of it, sell a few thousand of them, and go home, right? You never, ever, ever in a million years make back the money that it takes. It is on the order of hundreds of millions of dollars to get something like this out the door. It's a tremendous amount of money. It takes an incredibly large amount of software and hardware development, and then the initial manufacturing investment. You look at these fabrication facilities from the likes of TSMC, and these are multi-billion-dollar buildings using multi-tens of millions of dollar machines to fabricate these chips, and what you end up with is something that's 800 square millimeters worth of silicon that can run terabits and terabits of data.
I have just a quick question regarding this. How have the general purpose CPUs have also, let's say, developed a lot? Yeah, a lot of the functions that we were doing back in the days on, let's say, specialized ASICs are now super nice implemented on general purpose CPUs. How has this influenced your, let's say, building process? You also have to plan, what can I do on a general purpose CPU very good? So, I don't know, I make an example, encryption, yeah? Back in the days we had specialized chips for that. Now the modern x86 have catched up with these functions. Do you also have to consider what can maybe the general purpose CPUs do in, I don't know, 5, 6, 10 years ahead?
So we do, and one of the challenges of putting these systems together is that the network people primarily think in terms of bandwidth, and the CPU people primarily think in terms of operations per second or cycles per second. They're orders of magnitude different. I think the really, really high-end x86 forwarding paths will do 10-ish gigs on a core. Yeah. And we're talking about systems that do 200 terabits. So the difference there is, in my universe, software forwarding doesn't exist. Okay. What we have done, and will certainly continue to do, is if you start drilling down into the different blocks inside the NPU, almost all of those functionalities were things that at some point were too complex to do in hardware. The lookup tables, the data structures, more and more things, just like the CPU universe, more of those things have been implemented in logic and then integrated directly into the NPU. And it's that combination of things that let you do the features at terabit scale. That said, there are certainly still plenty of things where there's no hardware support for it. Some of it because the algorithms are complex enough that it just doesn't make sense. But a lot of that technology ends up being integrated into silicon over time.
Okay. So. You said the new routers don't always have all the features of the old ones. Do you have any kind of example for that?
The list it's probably too long to get into here in terms of what features are delivered when and where. Generally what happens is you got to crawl before you can walk from a forwarding plane standpoint, and why do you do IP and MPLS first? Well, because A, that's what most people want, and B, it's because you can't do BGP policy accounting until you can do all the forwarding that makes on top of it. So a lot of it is just around the idea of what order do we implement things in, and then you can get into things where as you get faster and faster, there are, the old, almost anything that requires stateful or deep packet inspection. If you're going to build an NPU, if you're going to build silicon that can look really, really far into the packet, you're paying that cost every time you switch a packet, right? If I say I want to be able to look at, 1,000 bytes into the packet for whatever key fields are there, I've got to carry that data through the entire pipeline. So whether I use it or not, I'm going to be burning those wires. I'm going to be burning those gates. And for ultra fast systems, the trade-off just doesn't make sense. Nobody's interested in me adding 50% power to the NPU so I can do a stateful inspection feature. Everybody wants the feature, but when you look at what that trade-off is going to cost, especially at really high speeds, the math just doesn't net out to where people are ultimately willing to pay for it. So a little bit of history on the system. 2020 now, we started this plan about 6 years ago. Again, sat some really, really bright people down in the room, said, what do the systems look like now? What do we think the systems are going to look like then? What sorts of physical constraints, what sorts of mechanical constraints are we going to have building the system? We acquired a company called Leba Semiconductor in 2016. This is the group that did the core intellectual property on the ASIC. We did the QSFP DD MSA in 2016 for the optical modules. Fast forward 3 or 4 years, a ton of hard work by a really large group of people, and then shipped the first platforms to the customers, I guess now 3 or 4 months ago, and then did the formal launch last month from San Francisco, where Chuck and a bunch of guys got up on the stage and waved hands and showed off what we'd all been working on for 5 years. So. All right, so same overview here. Najib covered the systems here. The 2 fixed systems, 1 RU, 2 RU. The product numbers are not the number of rack units. They just happen to be so for the first 2 systems. The 8203 will be a 1 RU system, for example. And then in the 8800 series, this is the modular distributed chassis. The number there is just the number of line cards. So one of the kind of guiding principles when we started doing the development was we had access through the Leba acquisition, had access to a chip that could function both as a standalone processing unit for a fixed system, also as the forwarding NPU for line card based systems, and also as the fabric interconnect for these larger modular systems. There's lots of technology and supply chain cost benefits to being able to use the same silicon in different parts of the system. So you get to amortize some of those really, really high fixed costs for silicon over multiple uses throughout the system. So one of the things we talk about is the 8000's really the first completely new router design we've done in about 15 years, 16 years now, I guess. You look at kind of the legacy of big routers inside Cisco, and I'm pretty old at Cisco. I'm not old enough to have been around for the AGS, but I am old enough to have been around for the 7000 and the 7500, and then the VIPs that went into there. That was all kind of one very similar architecture. It was all software forwarding. In 1998, we launched the GSR, which was the first really truly modular switch fabric interconnect system on the market. Did 6 different, meaningfully different hardware engines on GSR, where that architecture, that switch fabric scaled from 2.5 gig per slot in its first incantation, which is almost impossible for me to imagine, all the way up to 40 gigs per slot by the time the product was done there. In 2003, we launched the CRS, which inherited a fair bit of software technology from the GSR, a completely new network processing unit on the CRS that became CRS3 and CRSX. We took the NPU technology from CRS and used it to build the NCS6K, took the fabric interconnect from the DNX group and built the NCS6K out of that, built the 2 terabit line card on the NCS6K. In 2008, we took the Nexus 7K fabric and a customized EasyChip NPU, turned that combination into the ASR 9K, and then have run through now the 5th generation of line cards and silicon on the ASR 9K. 2015, 2016 in the XR universe, we've built merchant silicon-based systems for the 5500, which is the modular system. This one's based on Jericho, Jericho Plus, Jericho 2, and then the 5000, the NCS 5000 system, which is based on the XGS series silicon from Broadcom. So on Spitfire, on the 8000, we've gone and taken a completely new NPU, what we got from the Leap acquisition, some meaningful changes in the software universe with iOS XR7, and put those together to create the 8000 series. So the zoom in close up, top system here is the 1RU. This is the 8201. This is 24 by 100, or sorry, 24 by 400 plus 12 by 100. The 2RU version on the bottom is the 8202. It's exactly the same chip. If you look at everything other than the mechanical design, it's basically an identical system. We took the same number of SerDes, the same number of links, and basically did the internal mechanical breakouts differently to optimize the 2RU system for 100 gig density rather than for 400 gig density. So that's really about the only change or the only difference between these two systems. The 8800 series, the front view here, this is the modular system. There are 2 RPs, redundant RPs, run XR. In that regard, the software architecture, the software model, if you will, looks very similar to the other distributed XR routers that we've shipped in the past. And then the 2 different line card types up here on the top, picture the 48 by 100 gig card. If you notice the vertical pitch of the systems of these line cards is a little bit bigger than what folks are used to seeing on like the 5500 or the ASR 9K. And there's kind of 2 reasons for that. The first being we wanted to be able to build the 48 by 100 from a physical standpoint, and this is how much space you need to put the optics in there. We also wanted to, because we were looking down the road, and again, these were decisions made 4 and 5 years ago, looking down the road at wanting to be able to do very high power, long range 400 gig optics. And you're looking at power modules, 20 watts doesn't sound like a whole lot of power in most contexts. When you start talking about putting 36 of them in something that's only about that big square, it's an awful lot of power. And when router nerds say power, what they almost always mean is heat. So we have to look at the mechanical design to be able to take those optics. We want to be able to put any of those optics into any of those modules, into any of those plug holes at any given time. So mechanically designing the system to have sufficient thermal capacity is pretty important there. So if you look at the back of the chassis, the fabric cards go into the back, the fabric cards go in vertically, the line cards go in horizontally. We borrowed the orthogonal design from the NCS 5500, and then the fan trays go behind the fabric cards and pull air through the front. The power connections are in the back. The power modules get added and removed through the front. All of the modular systems have 4 fan trays. All of the modular systems have 8 fabric cards. One of the things we paid a lot of attention to when doing the design was we wanted to make sure that people had enough flexibility to populate the fabric however they wanted. So we have customers and use cases for 4, 5, 7, and 8 fabric cards. Obviously, you have more fabric cards, you get more bandwidth. If the system is only populated with the 100 gig cards, which is probably a fair bit of the market for the foreseeable future, those you only need 5 of the fabric cards to provide a fully redundant system. So if you've got a system with 5 fabric cards and you shoot one of them in the head, all the 100 gig cards are still going to be able to run wire rate every port all the time on just 4 cards. As you move to the 400 gig line cards, you've got more uplink bandwidth. So you need 8 fabric cards for full redundancy. If you lose one of those, you can run the system at full bandwidth on 7. Most of the kind of other competing or alternative architectures we looked at don't do fabric redundancy in the sense that if you lose something while all of the cards are populated, you're not going to be able to run all that traffic. Some people need that, some people want that, some people don't. As if you explode the system out and you just draw all the NPUs and how they're connected, it's just a great big leaf spine topology inside the system. If you take the 18 slot system, it's 4 NPUs on each line card, it's 4 NPUs on each fabric. So you've basically got 32 spines and 18 times 4, 72 leaf NPUs in a great big 2-layer clove fabric. And then XR software wraps the kind of instrumentation and control system around that and makes it look like one router. But if you just draw boxes and lines on a sheet of paper, it's nothing other than a big leaf spine system that's been mechanically compressed. Block diagram of the system. Fan trays go in the back. They're in yellow. Fabric cards are in this salmon orange color. They're vertical orthogonal connectors to the line cards that go in the front of the chassis. The 2 block diagrams here on the right, up here on the top, there are 4 forwarding ASICs, 4 NPUs, and 36 QSFP DD56 ports. So each of these NPUs is wired up to 9 of those ports. All of the line cards have a standard x86 DRAM that runs XR. That looks very much like the other XR modular systems we've built. On the bottom here is the block diagram for the 48 by 100 card. 2 forwarding ASICs, 2 NPUs on this card. We obviously don't have as much bandwidth. We've got more physical ports, but we don't have as much bandwidth, so we don't need as much silicon to do the work. There's the MaxSec device that lets us do wire rate MaxSec on all of these 100 gig ports, and then there are 48 QSFP 28 cages on the front of that line card. All right, Cisco Silicon One. This is my baby. All right, so the chip basically attempts to walk the line between things that were formerly only in the domain of switching ASICs and things that were formerly only in the domain of routing ASICs. Doesn't do all of both. Nothing ever does all of everything. That's not a thing. The chip itself was a complete redesign. It was a startup that they got started in 2015. To be honest, doesn't look like anything that anybody's ever built. It was a different approach to solving a different set of problems. We'll talk a little more detail about how they did it, but it's incredibly impressive. It's 10.8 terabits. It will do 7.2 billion packets a second. You can use it as a fabric interconnect. You can use it as a line card NPU. You can use it in a standalone system. The external name for this is the Q100. So this is what's been shipped. If anybody wants to walk across the street, we've got a mechanical sample on a really fancy little light box over there. It looks like a great big chip, which from the outside is never all that impressive. But from the inside, it's pretty amazing. So I always make the joke that this is the 2-hour slide. I'm kind of an NPU ASIC nerd. This is the stuff I like talking about. So I'll try not to drive everybody totally crazy here. We built these spider charts, and if you look at when you start trying to build and design these chips, these are all the things that everybody wants, right? Everybody wants a system that is infinitely scalable, counts every single statistic known to man, is completely programmable, has very dense, very deep, very fast QoS, has an infinite amount of packet buffering, will go infinitely fast, uses no power, costs no money, and has more bandwidth than anybody will ever need to switch. Yeah, exactly, right? It's super easy. We'll just step through the matrix and build it. In reality, what we end up doing is making trade-offs in terms of which of these things we're going to try and optimize for. So these are all these are all spider charts that represent the trade-offs that were made by major silicon players in the market. So on the right side, if you will, I have 2 examples of what were traditionally thought of as switching SoCs. If you look at the things they optimize for, right, where it's bandwidth, power, packets per second, and you're giving up scalability, you're giving up buffering. In a lot of cases, you're giving up the ability to add features to it later. What you get out of that is something that's faster and cheaper and lighter. If you take the opposite approach to that and go over to the left side of this slide, you look at devices that are more optimized for and I hate the quote-unquote service provider versus data center market. Like, I hate that terminology, but it does translate relatively well. Most people know what you're talking about. So in the classic service provider space, right, they cared about really different things. right? These systems generally didn't go into the network in 2010 and get ripped out in 2012 when something new was along. These things went into the network, if you look back on things like the GSR, these things went into the network in 1999 and came out of the network in 2014. Right, these are systems where they want to put those systems in. They want to add features. They want to swap out line cards. They want the old line cards to work with the new line cards. Then they want the newer line cards to work with those old line cards. And everything has to kind of run for a much longer period of time. So you end up building the NPUs in really different ways, right? You have a lot more programmability. You have a lot more scale, especially because you don't necessarily know how the systems are going to scale over time. That market traditionally cares a lot more about QoS. They care a lot more about deep buffering. So you just make a different set of trade-offs when you're designing the chip. When we went and built this guy, this chart doesn't really look like anything else, right? It's a different set of trade-offs. One of the examples I use here is everybody gets the same amount of string, right? The current state of the technology building chips says that for a given instance, I can only put down whatever the hell it is, 700 or 750 square millimeters of silicon. Right, that's the biggest chip that anybody can physically manufacture. No matter what I do or how bright I am or what choices I make, I am ultimately limited to a certain number of transistors. And if I can't solve the problem in that number of transistors, the problem can't be solved. So in that context, kind of picking and choosing what things I want to optimize for is really, really important. And then finding one or two, and it doesn't take much more than about two, either algorithms or intellectual property blocks or whatever noun you want to use in that context, but finding one or two ways to do things meaningfully more efficient or meaningfully faster can drive really, really big impacts into how fast the chip can go. So when we look at the Silicon One architecture, the chart in the middle is, it's kind of a hybrid of these other things. It's not going to be, in absolute terms, it's not going to be quite as fast or quite as much bandwidth or quite as power efficient as a chip that is 100% optimized around those things, but it's really close. It won't scale in terms of fib or routing or stats. It won't scale to the extent that something like the ASR 9K or the CRS would, because the memory required to do that just drives too much cost into, or too much opportunity cost into the rest of the system. But we've taken choices that we obviously think are the right ones for a big part of the market, and we definitely think that that's the direction that things are going, just from cost pressures and power pressures. I have this conversation with people all the time. They're like, but I really like this thing that I used to have. And I say, we can give you that. Are you willing to spend 50% more in terms of power to get that? And used to be the answer was yes, because power wasn't terribly important. It just wasn't that big a number. Now it's that big a number, and people are starting to care an awful lot.
Okay, so the middle one is the one that you went for when it comes to features. What I find interesting is that PPS, packets per second probably, is like the only one that is like right on the outermost edge it can be, and that's only important for the upper right one. So the others weren't even close to that, so you must have made the decision that this is really, really important, even though it's only in one of them, but not the others.
Yep, it is, and the packet rate and the ability to do that processing it's important to some extent because it's directly coupled to bandwidth. So driving that bandwidth it kind of implicitly drives the packet rate. One of those two or three kind of key intellectual property advantages that we have in this chip is, and I'll show you a diagram of the chip here in a minute. On this chip, we've got 6 different forwarding slices, and each of those runs at the clock rate. Each of those pipelines runs at the clock rate, where the highest number I've ever seen on another device is 4. Clock rates are in the 1 to 1.2 gigahertz range. We run them between 1 and 105, depending on exactly which system it is. So having that kind of parallel slice architecture in the chip, I certainly don't get those packet rates for free, but I get them at a meaningfully lower cost than if I had to replicate the entire forwarding core 6 different times. One of the meaningful changes we do is we've got some really slick intellectual property around how these multiple forwarding slices can access the memory structures that store the information. And so a lot of that drives packets per second rate that generally you wouldn't associate with this much bandwidth. So the silicon itself, I think it's fair to say this is a merger of the 2 best silicon teams in the networking industry. The Liba team was the group that built the DNX chips that was Dune Networks, acquired by Broadcom. The Cisco silicon teams built all of the portfolio, the fabric for ASR 9K. It was the forwarding engines for the CRS and the GSR. So it's that group of people who've been combined into what is now the Cisco Silicon organization. The goal was to get capabilities that looked like routing at speeds and feeds and power that looked like switching. That same set of trade-offs. One of the ways we did that was eliminating all of the off-chip memory. We'll talk a little bit in detail. The memory bandwidth and the memory access rates, these things do not track Moore's law, right? They don't grow that fast. So as we try to grow bandwidth and capabilities at what looks like Moore's law, we have to find other ways to do that. And one of them is the cost and power and board space that it takes to put down a whole bunch of these off-chip memories is just more than you can afford if you want to go this fast. So this chip uses what we call a 2.5D design. It's the HBM, the high bandwidth memory, that lives on a silicon interposer that's directly connected to the main forwarding die. This is all packaged into a single chip. So there's a large silicon block that's roughly that big that has 2 of the HBM devices plus the main forwarding die. That lets you get the buffer memory, this 8 gigs of buffer memory, lets you get it physically closer to the main die without having to put that much memory into the chip itself. You could never fit that much memory onto a chip and run it that fast. And then we talked a little bit about the algorithms and the intellectual property that go into doing the forwarding. So that's kind of where the secret sauce is. We won't talk too much about that because it's the secret sauce. And then we will talk about kind of the multi-slice architecture and how you can scale the system, how you can scale the NPU up and down there.
I have one question to the buffers. Were you aiming for a concrete number, what kind of memory you would like to have in the chip? Or was it kind of, we put as much in as we can as a design?
So it's not as much as we can.
Okay.
Some of that is determined by what memory technology is available in the industry. There's no technical reason that I couldn't have put down 4 HBM stacks rather than 2 and had 16 gigs of buffering. The kind of the physics of the memory universe is such where you can put on the order of tens of megabytes of memory in the chip on the die itself. Obviously, to go from tens of megabytes to gigabytes is a couple orders of magnitude. The only way to kind of jump over that huge chasm is to go onto an external device. And so the HBM, those devices are manufactured by, it's a memory standard. It comes in the sizes it comes in. I think you could probably contend that 8 gigs is probably more than you actually need for the vast majority of cases. But that's what gets built. So that's what we use. You can't go and get a 512 meg HBM part. It just doesn't get built.
I can also understand when customers come to you with buffers, it's like religion. Some want really large, others don't care, and it's for you. Of course, you have to, let's say, serve many use cases, and then the end is a compromise, like you showed in the graph. Yeah.
So in the 8200 series and the fixed series, we run all of the forwarding slices on the chip in what we call network mode, which literally means you have external facing interfaces plugged into them. Being able to do the entire chip as a forwarding entity lets me build these very, very efficient single chip systems. for cases where a single system solves the bandwidth problem, like, meets those requirements, it's a binary order of magnitude more efficient in terms of power and space than anything else, because I get to save all the interconnect. Right? As soon as you try to take a system and make it bigger than whatever you can do on a single chip, now I have to build some sort of mesh or some sort of fabric of multiple chips, and the increase in cost and power for there is pretty substantial. So if you look at the block diagram of the chip, it's a 6-slice architecture. Each of those forwarding slices, we logically break it up into a receive path and a transmit path. There's what we call the SMS, the shared memory switch. This is the interconnect inside the device that interconnects the slices. So packet comes in on slice 0, wants to go out slice 4. We do the forwarding lookup, figure out where it's going, switch it across this internal SMS over to the other slice, do the transmit functions on that side, and out it goes. So if you take a bunch of these and you stitch them together like this, we have the same silicon, right, the same part, operating in 2 different modes here. In the line card mode, we take 3 of these slices and we run them in what we call fabric mode, which is an incredibly original term for the forwarding operates as a switch fabric rather than as a network-facing port. And so if you kind of unfold this picture, you end up with that leaf spine topology that I was talking about. So if you put 32 of these fabric chips in the middle and you put 72 of them on the outside, now you've got either a folded or a wrapped leaf spine architecture here. So from a scalability standpoint, I can wire up, hundreds of these things, and I can put them in a modular chassis if I want, or I can take them and wire them into a whole bunch of small fixed boxes and build even larger networks that way, right? The hyperscalers build systems primarily out of small fixed boxes because there's no such thing as a modular box that's big enough to do the kind of bandwidth that they need. So the kind of main architectural trade-offs or architectures, if you will, that we're going to talk about. There's 3 that we're going to compare, and one of the big parts about this is, none of these are clearly better than the others for all cases. That's not the way the world works. You can optimize things for, you can optimize these chips for different functions. You make different trade-offs in what we call, and I don't pretend that these terms are absolutely perfect. They're just the terms that I choose to use. So don't give me too much of a hard time about that. In a very, very highly optimized system on chip type NPU, you've got a relatively rigid pipeline. These systems are designed to operate as standalone chassis, right? They don't have VOQ-based traffic managers. They don't have intelligence. There's no protocol built into these devices to ask another chip, hey, how many buffers are you using? Because I want to do allocation more fairly, right? There's less interaction there. When you start looking at the hardware blocks of the system themselves, they're much more tightly coupled. Right there, the analogy I've used in the past is you can bolt things together and you can weld things together, right? And it's more efficient to weld them together, right? You don't have to pay for the bolts, but then you can never, ever, ever get them back apart. So these, the blocks inside the chip are very, very tightly coupled. They, the entire thing is kind of designed together. You often, to scale the system up, the way we've done this for the last 6 or 8 years is we've taken a forwarding core, and basically you get smaller process nodes, the chip technology gets better. You take one of those cores, you stamp out another one. And it's great because you can do this now in the same amount of silicon footprint, and you get 2x the bandwidth, or maybe you get 4x the bandwidth if you're willing to put down 4 of these cores. It gives you the highest amount of bandwidth and generally the best power. The downsides to this are you've got to fit everything on the chip. So you've got to do all your forwarding tables, all of your lookup tables. If you want to do ACLs, if you want to do TCAM type lookups, you've got to have all of that silicon's got to live on the die. Again, you're constrained at how big that die can be. So you end up with this kind of really tightly coupled, optimized for a very specific set of things. Generally speaking, whatever the feature set is when it ships is the feature set you're going to get when it's 3 years from now. And then the canonical example of this would be the XGS line from Broadcom, right? It's that traditional switching silicon. You look at kind of the other, another point on that triangle, if you will, what I've called a pipeline SP looking architecture. And this is where you've made some changes in kind of the underlying assumptions or requirements, right? You want to be able to build a bigger system, and you want to be able to communicate state back and forth between different NPUs, right? So if you're trying to build a scheduled VOQ fabric, the chip on the right side of the chassis has to know at least something about the state, about the Q state on a chip from the left side of the chassis. So you have to build traffic managers and scheduler hierarchies that keep track of all that state to implement kind of system-wide QoS rather than ships in the night queuing, if you will. Most of these are still pipelined. They're generally still tightly coupled in terms of, stage 2 comes after stage 1. You can't change that order around. If you end up with some feature requirement where if you have to do some feature that requires information you haven't already computed, then you're going to have to either just live without it, or you're going to have to loop the entire packet back around, and that's relatively painful, both from a software development and a bandwidth standpoint. The current state of the art here is that these have 2 cores that share some set of the resources and replicate some set of the resources. What you get out of here is generally much higher bandwidth than you get on kind of a legacy service provider type NPU, but not as much bandwidth as you get on the system on chip. Excuse me. The designers here will generally allocate a little bit more of that silicon space for the on-chip lookups, for the on-chip TCAMs, and then depending on where you're building it, a lot of times we'll have the ability to add an external TCAM device. People like Broadcom make these external TCAMs. You literally wire the external TCAM onto some of the ports that the NPU would otherwise use for network or fabric interfaces. So the advantage of this external TCAM is you get a lot more space to do FIB lookups or ACL lookups or classifiers or policers, but you're using bandwidth ports that you would use otherwise to do that lookup. So it gives you more flexibility when you do the hardware design, but those TCAMs are very large, they're very expensive, they use a lot of power. So you got to make sure you really need that capability before you kind of jump off the bridge and spend that money. So the kind of this hybrid model that we do with Silicon One, the forwarding engines themselves are built out of a set of run to completion stages. So what this means is that I no longer have to worry about having stage 2 be a different hardware block than stage 1. Right? I've got some finite number of clock cycles that I have to do the math, but I can do them in whatever order I want. Right, so within one of the engines in the chip, I have the ability to do these features in different order. When customer A swears on their life that doing MPLS inside GRE is the holy grail and that's the way they want to do it, that's okay. When the other customer turns around and says, no, it has to be GRE inside MPLS. And if I've got something that's welded together and expects one, it's very difficult to do the other. If I've got 2 stages and I can program them to the sense that I don't care which one I do first, it gives me a lot more flexibility in terms of how I can deliver those features. One of the kind of meaningful changes or meaningful advances, I guess, if you will, is the engine that lets me do this sort of architecture that's not terribly larger and more expensive in terms of silicon than welding everything together, right? It's not free. I pay something for that ability, but one of the reasons that the chip was so impressive is that you have the ability to do that kind of, it's not arbitrary, that's the wrong word, more flexible ordering of features without paying a terribly high tax on it in terms of silicon.
Just to clarify, so in one process, when it goes over the chip, the long pipeline, you can switch what is done in which order, and how long is your pipeline? So how many steps you can do?
So what it lets you do is it lets you build. Sorry, can I get a time check real quick? Just see what the clock is. Great, thanks. I can build an almost arbitrarily long pipeline.
Okay.
Right, because I've got a run to completion engine where if I want to, I can say, just do some more work. Just go do another TCAM lookup. Now, I may pay for it in terms of performance, but I don't have to recirculate the entire packet. So it doesn't cut the bandwidth. The traditional way to solve this was I had 3 stages. I couldn't get it done. I need to do some more math, so I loop the packet back around,
Exactly.
and now I've forwarded the entire packet again. I've queued it again, I've burned all the bandwidth again, I've done all the memory accesses again, and it's a relatively coarse mechanism to do that. So what I get here is the ability to do a much more granular allocation of forwarding resources to the packet. So if
So you have the flexibility in the order and the flexibility in the steps that you would like to accomplish. Yeah.
Yeah.
Wow.
Yeah,
That's
I can write.
amazing.
I can write a block of code that says, do some lookups, do some math, do some stuff. Those aren't strictly wired the way they used to be. I can say again, I can do the MPLS part first, then the GRE part, or I can flip that around.
And if you need less number of stages,
Right.
now
Yep.
you have less power.
And if I imagine I have a contrived case where I have an interleave set of packets where the even packets all need 5 instructions and the odd packets all just need 1. Now my average is 3. In a legacy architecture, I had to do exactly the same thing to every packet. So I either, if the pipeline was 3 stages long, half the packets had to get recirculated. And if the pipeline was 5 stages long, then everybody would run at rate, but now I'm wasting all that resource for the simple packets. So here I get to recover all those resources that I don't use on the simple packets.
Wow, this is really, let's say, a kind of a game changer to the whole architecture.
From an architecture standpoint, it is. It's completely unlike anything else that exists. All right, some of the things that we kind of looked at in terms of, what makes this shit hard, right? We're trying to chase Moore's law because compute runs mostly at Moore's law, but the pieces we're using to build these systems don't grow that fast, right? We're trying to do a 4x bandwidth leap in about 3 years. You can't just do a new chip, right? You've got to have memory technology. You've got to have enough internal bandwidth to move the data around. You've got to figure out how to get this much power to the components. You've got to turn around and figure out how to get the equivalent amount of heat off the components, right? Because every watt, physics say every watt that goes into a system comes out as 3.41 BTUs worth of heat, right? There's no way around that. That's a law of physics. If the system uses the power, the heat's coming out. I got to get rid of it somehow. So we have spent an increasing amount of time doing kind of thermal and mechanical designs for these systems compared to what we did in the past. And then I'll let Mark talk about the optics, because trying to grow the density of the optics is every bit as important as trying to do it in the silicon. We got to have memory, right? I got to store state to do packet lookups. I got to worry about the physical size of the memory, how many bits, how many square millimeters, what sizes and shapes of memory can I either integrate into the silicon or can I buy from somebody? How many operations per second, right? This is a huge challenge in networking because the commodity DRAM memory that's used in servers, which is obviously what dominates the memory market because the volumes are astronomically high, it's not remotely close to fast enough for the stuff that I want to do, right? I want to do 7.2 billion packets a second on a chip. Each of those packets has a couple dozen memory accesses. You do the math, pretty soon you're approaching 1 trillion memory operations a second. Server memory is not designed to do that, right? So I either have to put SRAM down directly in the chip, or I have to use something like HBM to kind of bridge the gap between the on and off chip memories there. I got to try and get rid of as many accesses as I can, right? To go 7 billion packets a second, I can't spend very long on each packet. So I've got to have the right design of both memory types and memory layouts and do some really, really slick algorithmic magic as to how I'm doing all these lookups to make the router go fast enough there. So I got to worry about how do I get the signal, especially as we start doing high speed, right? Doing high speed signaling is an incredibly difficult part of what we do. I do not have a double E. I also do not have a degree in optical physics. I'm a computer science graduate who spent his entire career managing and troubleshooting networks. So to quote whoever was famous, any sufficiently new technology is indistinguishable from magic, something like that. The signal integrity piece is magic to me. The short version is the closer you put things together, the easier it is. As you start dragging them further apart, you have to do all sorts of fancy math, and when the math starts using Greek letters, that's usually where I usually get off the train. But we do spend a lot of effort on optimizing the systems around. You can solve some of this if I've got a trace that's too long to drive a signal from the NPU to the optic. I can just put a retimer in there, which literally regenerates a signal. That's great, except those retimers cost money and they cost power and they take up space. So one of the things that I will contend that Cisco does better than anyone else alive is the physical design of those boards and how I can build a board that's the size and shape to meet the bandwidth I want while minimizing the additional amount of the additional devices that I have to put down on the board. A huge part of this is all driven with the motivation of reducing the power of the system, right? We've got a 10 terabit router, switch router, whatever the hell you want to call it, that will run in about 415 watts, right? You can make coffee with less power than that. The 100 gig version runs in about 750 watts. One of the things that you will see is we have stopped including the optics power in the system power numbers. And we're not trying to cheat, we're not trying to be devious, we're not trying to get away with anything. In the old days, when I might put 12 optical modules on a line card, and those optical modules were 3 watts each, nobody really cared whether we were adding or subtracting 35 watts power. 36 ports on a line card, 20 watts per optic, that's 720 watts just for the optics. So there's no, the variance in optics power, the number of optics we're looking at is now high enough that I can't make any assumptions about what people are going to use, so I'm just taking the numbers out and telling everybody. The power design, there's a ton of work that went into, again, I got to get all this power I got to get it off the utility. I got to get it into something that cleans it and turns it into the right voltages, and then I got to get it to all the components. Go across the street, look at the chassis. The bus bar in there is about that big around. It has to carry a tremendous amount of power. But there's a ton of little improvements and little innovations that go into the mechanical design of these things that I try to give the engineers a shout out, because it's kind of hard, invisible work that they do a lot of work on, where if I can take out one voltage conversion step, maybe that's 3 or 5% efficiency for that little part of the design. And yeah, on a 1,000 watt line card, 3% is 30 watts of power. 30 watts of power is not that much power, but 30 watts of power times 18 line cards is 500 watts of power. And if I can do that 2 or maybe 3 times, pretty soon I'm talking about enough power that's one less module I've got to wire. And if those power modules are several hundred to a couple $1,000s a month, just in terms of what you got to pay you got to pay the colo or you got to pay the utility, ends up being a lot of money. Tons and tons of work went into, you got to get the power in and then you got to get the heat out, right? You've got all these different components, right? The chips, the memory devices, the optics, all of them have some set of temperature range that they can operate in. Some of those ranges are really different. So you have to kind of engineer different parts of the system to be cooled to different temperatures. You've got issues where, the air comes in the front of the chassis, comes over the optics. If the optics are using 700 watts of power, now I've added 700 watts of heat to the air that came over those. So all the downstream devices are now dealing with warmer air. So inside the chassis, I've got to do both thermal modeling and engineering to take all that heat and, I've got heat sinks where I can spread it out. I've got to try and get it conducted into the air, and then I've got to get it back out of the back of the system, preferably without melting whatever's behind it. Although sometimes we don't care.
One question. Is it always front to back or back to front, or can you switch the cooling flow?
In the modular systems, it's always front to back. In the fixed systems, you can flip the fans. Now, that said, if you flip the fans to where the optics are on the downstream side, it has to be cooler in the room. The max ambient temperature changes if you invert the fans.
Okay.
So to give you some idea of how much power we're looking at here, how much component here, a fully loaded chassis is 20 Xeon server class CPUs. It's 576 gigs of buffer memory. It's 640 gigs of DRAM, and it's over 5,000 lasers. So all of this stuff goes in there. All of it's generating heat. All of it's using power. It's doing it in different physical locations, even within the device, right? We're to the point now where I can't take the NPU, it's roughly a square inch. I can't take the NPU and treat it as if it's a uniform temperature because there are parts of the chip that are hotter that generate more heat than the others. So I've got to not only do a design for the total thermal power, I've got to do a design that can handle whatever the hottest particular spot on the chip is. So I've got all this work. You've got different optical modules that have both different amounts of heat that they generate and different amounts of power that they require. So I've got to engineer for all of that, and all of that work kind of goes into the mechanical design.
And if you do it wrong, the longevity of the ASIC will.
Perfect. Right. I had a slide on optics. Mark's going to do the optics piece. So that's the end of the NPU nerd part. So. Questions? More questions?
What's the positioning of Silicon One beyond the service provider network? Is this the new architecture that's going to bleed out into the data center, high-end enterprise? Is this something that's going to be pervasive?
Sure. So I can't talk in terrible detail about that, but I'll joke. We didn't spend that much money on a company to just use it in one part of the network. Mm-hmm. That technology, will certainly find its way into other parts of the network. It will certainly find its way into other Cisco products. As we announced last month, it will also find its way into customer networks who want to just consume the chip. Mm-hmm. Right? You don't have to buy a complete system, full stack system anymore.
This could be a component of a white box platform. I've been reading about that.
Yeah, and that's we're now publicly open to the idea of selling different levels of the stack to different people. Now that said, I do think there's a lot of hype around people wanting to build their own systems who have no idea how hard it is. Mm-hmm. But that aside, we've announced that we're open to that. We've been open to that for a while, but now we've announced it.
Now you're playing in Broadcom's game as well.
Yeah. And that's we've had a number of those customers who want, they want silicon diversity, they want system diversity, they want software diversity. The nice part about my world is that I'm kind of the only people that can sell them all of it. I don't have to sell them all of it, but we can play everywhere.
That's very cool. So, but still mostly at the high end, or how does that?
Mostly at the high end.
Yeah, so UADP still has its place, and the Silicon
for sure.
One's at the higher end of it, and maybe there will be something in the middle. Who knows? Yeah. Okay, thank you.